Controlling objects is something that is already available everywhere. But in this department, we are controlling flying vehicles. So that's very special. It's a very specialized area. Which actually means that we will be controlling the flying objects. Therefore, we need to understand the dynamics of flying objects. And when I say dynamics, I mean motion. Right? We need to understand the motion, how it moves, how something moves in air. Okay? In aerodynamics classes, you have learned how you produce lift, where drag is coming from, where moments are coming from, and all these things. Hurry up. We made a deal that after 9:45 you will not come to class, okay? Next time. So 9:45 is the deadline. If you come after 9:45, don't open the door, all right? I will start 9:45, so don't come in after that. So therefore, the flight mechanics part is important if you want to do controls. That's what I'm trying to say. I mean, flight mechanics is important for a lot of things, but it's especially important if you want to do controls. If you want to design a controller for an unmanned vehicle, if you want to design the autopilots for airplanes, for helicopters, for satellites, rockets, you have to understand the dynamics in order to design a controller. Otherwise, you can't do it. And this is probably the first step in trying to understand how airplanes fly. Understanding the dynamics. Okay? Okay, this is just horrible. Just go in. Yes. And see, I forget what I'm saying. You had system dynamics. That was a start. And we will be using system dynamics in this class. How many people did not take system dynamics? Okay, so we'll see. Look at the first 2 weeks of this class. Okay? The first 2 weeks. If you understand everything, that's fine. If you don't understand much, you need to think about it. All right? Because system dynamics is used to analyze those dynamic systems, so we will be using some concepts at least from system dynamics. Okay? But if you haven't taken it, it is not horribly bad. I think you can understand it's not too horribly bad. All right? So let's go through these topics real quick. As I said, my name is Ilkay Yavrucuk. This is my email. The best way to reach me is sometimes by email, especially if you want to talk to me and you want to arrange a meeting with me. Okay? Please send me an email, and we can all meet and talk. My office is in this building. It's 102, Aerospace Engineering Building. The graduate assistant right now is Hazal Altu. There might be one more assistant. If that will come along, I will let you know. And you will be able to ask questions to them at first. And then they will also be correcting the exam, not the exams, but the midterms. Not the midterms, but the homeworks. So you can ask questions and go back and forth. Website, this is our website. It's on the departmental website. I will announce homeworks and things like this on the website, so that will be good. Topics. Well, I have 7 major topics here. The first one is introduction, and that introduction will take 2 weeks. It will be this week and the following week. The second one will be definitions, coordinate systems, Euler angles, transformations. This part is very important because it defines the language that we will be speaking together. Okay, these are definitions of angles, coordinate systems, reference frames, and things like that, so that when I tell you about a coordinate system or we talk about an angle, we all know what this angle is or what that coordinate system is. So you have to understand or fully understand what these angles or coordinate systems are so we can talk. If I tell you the pitch angle is such and such, you need to understand what it exactly means. Okay? Number 3, aircraft equations of motion. It is sometimes known as the 6th degree of freedom equations. Okay? Again, very fundamental. As you might think, airplanes move in 6 degrees of freedom. Right? The three of them are basically the linear, linear motion, like forward, side, downwards. And the other three are the angles, right? Roll, pitch, and yaw. So if you add them together, you have a motion that looks something like this in space, but it is a motion in 6 degrees of freedom. So we will be writing the equations that define this particular motion in 6 degrees of freedom. So if you have these equations written, what you will see is you can describe with those equations the motion of the aircraft. After that, we will be talking about trimming. You probably know already what trimming is, but you will see another approach over here. And then we will talk about linearization, a very important part in the analysis in flight mechanics and control. We like to linearize things. Why do we linearize things? Because they are simpler, right? Once you have a linear system, it's simpler. Then you have a big matrix and you can play around, you can do a lot of things. Fortunately, the fixed-wing airplane is quite linear in nature. Remember the CL alpha graph. It goes straight up and then has a little curve, which is the stall region. So if it's not installed, it's pretty much linear, isn't it? So which means the system is already linear. That is not true for helicopters or quadrotors. Right? They're quite nonlinear. So what you do is you linearize around a certain point and so on and so forth, and it has its own benefits. We will talk about that. Number 5 is, it's a small gain approach. You can linearize things in different ways. I will teach you a few different ways how you can do it. But one of them is the small gain approach. It gives you a different perspective to linearization, and that's what we are going to do here. Aircraft stability in steady flight. So the most classic flight condition is, of course, the steady flight condition, right? The airplane flies just steady and trim. So we will analyze that because we are interested in the stability of that vehicle in steady flight. If you think of a passenger airplane, the airplane flies maybe 80% of its time in steady flight. So you want to have it stable. You don't want to have it moving too much. But if it's too stable, then it will not move at all, which is again quite bad. So these are the things we will be looking at in aircraft stability for steady flight. We'll look at longitudinal flight dynamics. Longitudinal means if you look to the airplane from the side, this will be the dynamics looking from the side. Lateral flight dynamics is if you look at it from the front. Okay? The nice thing with fixed-wing airplanes is you can separate them, the longitudinal and lateral. The action of the lateral to the longitudinal or vice versa is quite limited for airplanes. So we can make an approximation saying that we can look at the longitudinal dynamics first, and then we look at the lateral dynamics, and we look at them separately. Again, this is not something you can do with helicopters, for instance, but for fixed-wing airplanes, we can do it. So as you see in the topics, we will be mostly talking about fixed-wing airplanes. Okay, not about helicopters, not about space vehicles and stuff like that. If we have time at the end, I have done this in the past. Let me move it here. Makes a lot of noise. Okay. In the past, I used to try to teach a little bit of helicopters and a little bit of spacecraft at the end of the class. And I will still do that if we have time. I just took it out from the topics list just to reduce anticipation. Okay? So we might still cover a little bit of helicopters and space vehicles. Okay, grading, we will have 2 midterms, 1 final, and we will have some homeworks and hopefully some lab. Okay? The lab will be kind of a demonstration, or it will be part of the homework. Typically, we have about 3 to 4 homeworks. Okay? The homeworks are sometimes a little long, and sometimes you have to really sit down and think about it. The reason I'm doing this is the subjects that we are teaching here, they are hard to handle if you just memorize things. You have to visualize and understand. And that requires a little bit of training. Okay? And that training comes from looking at problems, thinking about them. When I say they are difficult or they are a little long, I don't mean they are tricky. I don't like problems that are too tricky, meaning that there was something hidden inside or something, you know, you have to discover. No. It's just a typical thing. An airplane is making a turn, trying to land on a ship, something like that. But I want you to fully understand those things. Now, if you understand the homeworks, if you understand them and you can do them, that means in the midterms you will probably be also very successful. At least this is the experience that I have in this class. I've been teaching this class this is the 12th time. So I've taught this class more than 10 times before you. So I have some experience, okay? So if a student understands the homeworks, he or she will probably be also very successful in the midterms. But if you don't understand the homeworks, then it will be quite hard, okay? So at the beginning, when we teach the class, the subjects might appear even easy. I have a lot of students who tell me when they get out of the class, they have understood everything. And then they come back in 1 month and say, everything, I'm so confused, everything is now spaghetti. Okay? So what you need to do is you need to do 2 things. Be in class. Secondly, go home and review. 3, do the homeworks. Okay? Then at the end of this semester, you'll hopefully learn everything that's covered in this class. All right? A few things about the homeworks and the midterms. The midterms and the finals, I mean the exams, I prepare the questions from scratch. So they are not available in literature, in the internet, or anywhere else. I'm not asking questions from previous years. I will be redesigning questions brand new for every class. I did that and I will do it for you as well. Okay? So there's no room to memorize things. All exams will be different and new. I'm trying to do the same thing for homeworks. Sometimes the homeworks might be similar to previous years, but I'm trying to do as much as I can to do new questions. But that's not really the point. I mean, the point is that even if I ask questions from previous years, you have to be able to solve them by yourself or understand them by yourself. Which doesn't mean that you shouldn't talk to your friend. Okay? I mean, more oftentimes we have no way of checking if someone is copying from his friend or her friend. That's fine, actually. I'm not the police. I don't want to be the police trying to find who's copying what. Okay? But I'm just saying, if you want to learn this, you have to understand the homeworks. And if you copy from your friend and you don't understand the homework, you might get the 10, 15 points over there, but I guarantee you might fail from the midterms and finals. So you have to understand what's going on. And that is not possible just by reading. You have to think about it. You have to think about it when you go to bed. You have to think about it when you wake up. Yeah, you're laughing, but that's the life of an engineer. You have to think with problems. You wake up with problems and you sleep with problems. Okay? So that's it. You have plus minus 5%. That is because sometimes the whole class does bad or the whole class does very good, or sometimes one student might have a bad day for that exam day. So it gives me a little bit of flexibility playing around with those numbers. But in all these years, you know, very often, it doesn't matter how you put these percentages. A student's grade doesn't change that much. Okay? Doesn't change that much. If someone's grade is changing a lot by playing with these numbers, you know, 5% here, 5% there, then I take a closer look at the student. I say, okay, maybe the student had a bad day in midterm 2. Everything else looks fine, so maybe he should go to the upper bracket of grades, right? So that's my flexibility. But overall, you know, it's a whole thing. You do homeworks, you do midterms, you do final and all this. And it's always a nice trend for students. And sometimes I look, the student started not very good, but he or she got better and better and better throughout the semester, which is also an indication that was a slow starter, but at the end actually learned everything. Right? That's also something great. So that gives me a little bit of flexibility, but overall this will be the grades here. Okay. Before I go to textbooks, grading, not grading, attendance. Attendance. I don't take attendance, obviously, and you can be here as much as you want. My experience, though, is that if you want to learn this class, you have to be here. It's just an experience I had in the 10, 11 years. Okay? Because the subjects that we are explaining are rather hard to learn from books. I mean, you can read them, surely, and if you can learn everything just by reading books, that's fine. Okay? If you can do the midterms, if you can do the finals, if you understand everything, it's great. Most of the students cannot. They have to listen and they have to discuss, they have to go through that exercise. Okay? So I encourage you to come here. So that brings me also to that little camera at the back. This is going to be open courseware, which means it will be later in the internet so that people can follow this class from the internet. So every week we will be filming this and we will be putting it on the web, and there's also a chance that you might actually go back and listen to this class from the website later on. Okay, so that will be a benefit for you if you miss something. And dress nicely because you might be on camera, and in the next year people might be looking at you and you might be looking at yourself. Maybe comb your hair, maybe shave a little bit, I don't know, it's up to you. So that's the deal with the camera. Okay, it's going to be open courseware at ODTÜ. All right, textbooks. We don't really have one textbook, really. It's hard to pick one textbook for a class like that. If I had to pick textbooks, then I would pick these two. In fact, the first one is, they're both written by Bernard Etkin, with one is with a co-author, but they're written by Bernard Etkin. The first one is a 1972 edition book. It's very old, even older than I, believe it or not. So it's 1972, and for a while they stopped printing this book. Okay, they stopped printing this book, and a lot of people were looking for these old books, the 1972 books, because they were very popular. It was still one of the best books. And later in 2005, Dover Publications republished the book because there was such a big demand for that book. Okay? And Dover Publications sells it for a rather low price, and a lot of students they ordered it from Amazon, and they got it for this course. So it is not in the bookstore, unfortunately, but we talked to Dover Publications, by the way, and they said, you know, students just order our books. We don't provide them to bookstores, so I guess you have to download, order it if you want it. Okay, so that's that. Number two is Bernard Etkin, Dynamics of Flight Stability and Control. That's a book that was written in '96. It is a little bit more geared towards stability and control. Therefore, it is not as fundamental as the first one. It is a very good book. It is available in a lot of places. I also have seen it in the bookstore. So it is also a good book. But especially the first half of this course will probably be more from the first book, and the second half probably from the second book more. But as I said, I'm not really following everything step by step, but these books are quite nice books to read and to supplement this course. Okay? And if you find something that is similar in this course, it might be from that book. So these two books are very, very good. I have a few references. Robert Nelson, Flight Stability and Automatic Control. As the name suggests, it talks more about stability and control again, but it has a very good chapters on flight dynamics. It is easy to read, quite easy to read, and it was electronically available in the Meta library. I hope it still is. So it is something that you can learn, you can read before you go to sleep. Okay? Instead of reading Harry Potter, you might read Nelson's Flight Dynamics. Okay? Number 2, Brian and Lewis, very famous book, Aircraft Control and Simulation. It is a bit of an advanced book. If you want to build simulations for an F-16, for instance, that book would be really great. And it has a little bit more advanced information inside. So therefore, it is not a starter's book, but it's a very good book after a certain time in flight mechanics. So you might want to think of that too. Thomas Yeckhout, Introduction to Aircraft Flight Mechanics. This is an AIAA book. At first, the book looked very good to me, but I found some flaws in it. Okay, something that I didn't feel was okay or right. So I kind of put it at the 3rd row here. But it is still a nice book to have. Okay? So if you want to buy one book, it will be these 2 books. Okay? So, any questions? Is this good enough to explain the expectations, at least, from this class? Okay? All right. So, that means we are ready to start the course, introduction, number 1. So let me talk about introduction. The introduction will be rather a review of system dynamics. Okay, for people who have not taken system dynamics, it might be good. Of course, we cannot review everything, but it will be the parts that we really need in terms of concepts. I will review them this week and next week. So what we are doing in this course, in this introduction or in this review, is the following. I give you a simple example, which will be a simple pendulum. Not a pendulum, right? They swing back and forth with some friction, so they stop. If there's no friction, they will oscillate forever. So they will stop because there's friction. So we will talk about this pendulum, and I will go step by step and do an analysis on the motion of the pendulum. So if you understand what I'm doing there, I will do the exact same thing for an airplane. Okay? So for the next month or so, we will be just doing the same thing that I'm going to do for the pendulum, I'm going to do for the airplane. So if you don't understand the pendulum example, then you will probably be lost on the other side. And if you get lost on the other side, you can always go back to the pendulum examples, thinking that, okay, what are we doing in this thing? The teacher's writing and writing and writing. What are we actually doing? So you can go back to the pendulum and say, okay, we are trying to find the equilibrium points, and now we are trying to linearize it. Oh, okay, so how did we do it in the pendulum? We did it this way. So he's doing the same thing on this side. It just looks more complex and complicated because it's a more complicated flying object, obviously. Okay? So that's the thing. And if you feel that you don't understand some of those parts in this pendulum, then maybe you should go back and re-look into your dynamics book, or into your system dynamics book, or into your differential equations book, or something like that. Okay, you need to go back and look to them if you don't understand anything that I'm doing in this pendulum example. Okay? Ready? Okay, so let's start the course then. The way we are doing this is we are using this little device here. Hopefully it will work. Yes, it does work. It used to have a little lamp here, but it seems to not have it. Okay. Okay, the first class is always the most difficult one because you're trying to arrange things. once we have done that, I'm sure it will be easier next time. So let's start with this. AE372. Okay, you can't see anything. Okay, not bad. So the first topic is called Introduction to, or review rather, let's call it the review to system dynamics. Okay, so we will start with this following example and we will go through that one by one. Consider the following system. So the system will be, consider a pendulum. It just hangs here in the middle, and it likes to swing around, right? It likes to swing around. So it has a mass m, okay? This has a length of L. This is a length of L. And because it swings around, when the pendulum is over here, this angle we will call theta. Okay, this is the theta angle. Another thing I want to add here is I want to add some sort of a friction, okay, with a friction coefficient K. Friction coefficient. The reason I'm adding this friction is because if I don't have friction in the system, it will oscillate forever, right? If I start here and I'm going to leave it, if there's no friction, it will oscillate back and forth. So there must be some friction somewhere. And because it's friction, it will be a function of theta dot, the velocity, the angular velocity, right? It will not be, it is not a spring. If it was a spring, it would be a function of theta. What I'm doing here, because it's a friction coefficient, it will be a function of theta dot. So theta dot is d theta dt. So it is a time change of theta. So it is the angular velocity. Okay? So the angle, this will be a function of angular velocity, not of that thing. So this is my system basically. And what I want to do is I want to analyze the motion of this pendulum. And I want to do this mathematically. I mean, what does it mean, analyzing the motion? I mean, every kid will know that this will oscillate, and if there's friction, it will come to a stop, and it will stop here. This is not anything special, everyone knows that. But can we do this mathematically in a systematic way? Because if I can do this mathematically in a systematic way, it means I can do this for more complex systems, right? So that's what we're going to do. We're going to analyze the motion. Analyzing the motion also means analyze the dynamics. Okay? We will try to analyze the dynamics of this system. So here's my question. How do you analyze the dynamics of any system? Where do you start? Where did everything start? Where is the first glimpse of information that helps us analyze a dynamic system? Three-body diagram. Let's go back in history. Who was the person who helped us writing those equations? Who? Newton. I heard other things. Euler. I don't know. Newton, of course. It's Newton dynamics. When did Newton live? What year? In what time frame did he live? 17th, right? 17th. Late 17th century, early 18th century, right? 1700s. So he put together a way of thinking for rigid body dynamics, especially for particles. And we are still using that mathematics and that framework to analyze motion. So he has 3 rules, right? What's the third one? If you don't know the third rule of Newton, action, reaction, okay, what else do you have? Okay, let's tell all 3. Action, reaction, what else? Inertia, right? Things have inertia. They need force to move. What's the third one? The formula, what is it? F equals ma. Oh, God. Yes, F equals ma. I thought this was the most easy one, but it turned out to be quite challenging. So that's Newton's law. Okay. Very simple formula. It looks very simple, but believe me, a lot of students still get very confused. F is the force, m is the mass, a is the acceleration. Okay, good. So let's try to analyze this. So since it's a vector equation, this is a vector equation, you need somewhat a coordinate system somewhere, right? So what we typically would do is we put a coordinate system to this thing, call this thing x, call this thing y. So this will be our coordinate system on this thing. So let's try to write this equation. Let's write it at least in one direction, right? In either x or y, and let's try to analyze it. Before we do that, F is obviously the external forces that act on the mass. What are the external forces that act on the mass? Can you raise your hand and speak up maybe? Yes, please. Gravitational force. Very good. And that is mg. What else do we have? Can you raise your hand and tell me? Yes, please. Tension in the rope. Tension in the rope. So the rope is pulling this thing, right? So this is the tension. Anything else? Yes, please. And we have the friction force, right? So the friction force will be because of theta dot. It will be in this direction, right? I mean, wherever the motion is, if it moves in this direction, the friction force will be in the opposite direction. So it will be in the direction of x, we have the friction force. Anything else? That's it. Good. Very good. So we have 3 forces acting on this. These are the external forces. Okay? Let's try to write it first in the y direction. Okay? Let's look at the y direction first. Y direction. So we are going to write the forces in the y direction. What do I have? What are the forces in the y direction? Right? It's t. So it's a minus t because y is positive in this direction, so it will be a minus t. What else do I have? Mg plus or minus? Plus mg cos theta, cosine theta, right? Anything else? In the y direction? No, because the friction is in the x direction, so no friction. Then it's equal to m times acceleration in y. Is there acceleration in the y direction? No. It's on camera, so be careful. Is there acceleration in y? Please edit this out, okay? If this goes on YouTube, it will be quite embarrassing. Yes? Why? Is there acceleration in y? Yes, please. The rope length is constant, therefore, oh God. The rope length is constant, therefore there is no motion in this direction, and therefore in the y direction, therefore acceleration is 0. Is that the comment? You are a graduate student, so I want to check the undergrads. Yes, please.
So it's going to be v squared over f.
Where is that coming from?
This is the I think because of the I don't know the
Yeah.
ellipses, I guess.
Yeah.
In English, I don't know.
Okay. So there is some acceleration in this direction. How many people believe there is an acceleration in this direction? Let's just do that. Don't be like, maybe. Do it. Do it. So, and look around yourself. How many people believe there is acceleration in this direction? How many people there is no acceleration in this direction? It's a good number of people. Third year ought to. Very good. How does acceleration happen? What does acceleration mean? It is change in velocity. Okay, acceleration is change in velocity. It's change in the velocity vector, because the velocity is a vector and acceleration is a vector, right? So it is change in vector. Is there velocity in this direction? No. Therefore, the acceleration is 0. Okay, let's take this. Let's take this. What is the velocity of this thing? It's like this, isn't it? And when it goes up, what's the velocity vector now? It's like that, isn't it? Did the magnitude change? The magnitude? Yeah, magnitude changed, but not in this direction. But what's important is the direction has changed, right? And the directional change, let's call this V bar, and V prime and V. The directional change is actually in this direction. Because the direction is changing. The velocity vector's direction is changing from here all the way to here. It always keeps changing. And as it keeps changing, you get an acceleration here because the change in direction, there's a change in direction, see? Acceleration doesn't only happen when the magnitude changes. It also happens when the direction is changing. And the direction is definitely changing. So in which direction? It changes in that direction. So this minus that will give you this. So this is the acceleration. So you have an acceleration in this direction. Let me put it in another way. Newton says F equals ma. That means if there's acceleration in this direction, there must be a force in that direction as well, a net force. Okay? A net force must be also in that direction. Otherwise, you will not have an acceleration in that direction. So let me try to illustrate it in another way. Let's say you have an airplane. Okay, let's say you have an airplane. And let's say the airplane is flying at a constant velocity forward. So it's flying like that. Okay? Flying forward at a constant velocity. An airplane. Now, if you don't touch the airplane, it will keep moving in this direction. Right? It will keep flying in that direction. This is my little airplane that flies in that direction. If you want it to change its direction, what do you need to do? Someone has to pull this guy with a force so that the airplane will actually be pulled in one direction and it changes its direction like that. So someone has to pull him. can be Superman. He can just come, pull the airplane, and the airplane will change direction. So you're flying straight, okay? And someone pulls the airplane and changes direction. So I need a force to pull this guy. Force means, here, force means acceleration. There must be an acceleration in this direction. Okay? Even though the velocity of the airplane is constant, the direction of the velocity will change, and therefore there must be an acceleration because of this. Now that is true, of course, if there's a force. And every kid will tell me that if the airplane was going straight, someone has to pull it to change direction. Isn't that true? Isn't that true? If you don't touch it, it will go straight. Someone has to pull it with a force. It can be Superman. He can just take it and pull it. It can be something else. In airplanes, what we do is we take the airplane, we rotate the lift vector a little bit. The lift vector is pointing upwards, right? We tilt that airplane, and then part of the lift vector is pointing this way, and therefore you're turning. So that is the force that is pulling the airplane sideways. Okay? Now, if this force is momentarily, it will just, of course, turn direction, and then we'll start going straight again. Right? But if you keep pulling with the same force, it will keep changing direction. Keep changing direction, and you can actually make this airplane go in a circle, but you constantly have to pull it. If you stop pulling, it will just go straight again. Okay? Therefore, you need to pull this thing inside so that it stays in a circle. If there is force, there is acceleration. And that acceleration we call centripetal acceleration, and it is there because of the force. What does the force do? Does it change the velocity of this vehicle? Does it change the velocity of this thing? Doesn't have to. No, this force doesn't change the velocity. The velocity is constant. What is changing is the direction of the velocity vector. And that's the definition of acceleration. Change in velocity vector, the direction will give you acceleration. And if there's acceleration, there is force. Vice versa, if there is force, there is acceleration. You need a force in order to get that acceleration. So what does the acceleration do? It changes the direction of the velocity vector. And that force we call centripetal force, acceleration, centripetal acceleration. Is that clear? Is there force or acceleration in the y direction? Yes? Just say a loud yes so the camera can hear it. Yes? Yes, thank you. So we call this AY. And what you have learned in high school, mv kare bölü r, remember that? So that acceleration, in order to keep a mass in a certain circle of r, this is the acceleration you need. And we will actually derive this acceleration later in this class. Okay? This is something you learned in high school, but I'm not sure if you really derived it. But this is something you will derive. So in our case, AY will be equal to whatever that velocity is. What will be that velocity? That velocity will be, let's put it this way, velocity is equal to, remember this? Omega times r from high school? Right. Omega is the angular velocity. So the angular velocity will be equal to theta dot times r is L in our case. So this is your velocity vector. The magnitude of your velocity, theta dot times L. Okay? So writing this formula now in a clean fashion, let me write it in another paper. Write this in a clean fashion. This will be equal to minus t plus mg cos theta is equal to m times theta dot square times L square, right? Because V is equal to theta dot times L, and V square divided by L, V kare bölü R, divided by L, this is gone, and that's your formula, minus T plus mg cos theta is equal to m dot theta dot square times L. This is a differential equation, right? It's a nonlinear differential equation and describes the motion or the dynamics in y direction. Is that cool? Is that okay? So, let's give a break. In the next hour, I will write the equation for the x direction, which is even more interesting. Okay?